I find it interesting. I'm going to introduce a panel, most of whom I don't know and most of whom you all know, but this is a good opportunity for me, and I want to thank you for really keeping focused on the kind of things that we've been interested in. Once again, for coming back here. I'm going to be sorry to see you go, and I assume you're really not going, but we'll find out. But thank you again. It's really a pleasure. I usually like to make a vacation out of it with my wife. It's a good excuse to come to Wyoming, and then we take off, but it didn't happen this time, so I'm working. You know, we got a tremendous panel up here, and the topic is the value proposition for delivering Wyoming wind to California. I thought, well, what's the value proposition? What's the value added I'm bringing? And the only thing I can think of is that I'm from California. And that's a whole different world out there. They speak a different language. And I'm basically a political person. I am a labor person, but I do politics. So I don't know if any of you have ever seen the Key and Peele comedy routine with the president, where he has an anger translator behind him, and he gives this very cool, collected speech about, you know, some really hot topic, and the anger translator's pacing back and forth. And while the president speaks very calmly, he's back there going, and damn it, that's right, and he's telling everybody he's translating the anger. Well, I'm sort of the California translator, because it is definitely a different world out there. I was thinking when you had your last presentation, the coal industry, these are some incredible projects you're talking about. But if there's a put upon industry in the United States, coal has to be right at the top of the list there. Talk about not politically correct. And that equals tremendous opposition to whatever you're doing. Even if it's perfectly politically correct, it just never gets to that point, and it's quite baffling. But wind, on the other hand, is completely politically correct nowadays. But in California terms, you're completely politically correct, but it doesn't reduce the opposition. So it's hard to figure out any of this stuff, especially from California. By the way, I'm from New York. Anybody from New York here besides me? One? Okay, I'm in a little trouble, I can tell. It's going to be interesting. Anyhow, I want to get to the topic because we've got people here who are really, really knowledgeable and make a very compelling case, and again, most of whom you know. The first one is Dr. Jonathan Naughton. I read through the bio a little bit. I've met him once before. Just stay over there. We're going to work from over there and make it easier so everybody doesn't have to go back and forth. So he's been here since 1997 at the University of Wyoming. I'm sure you all know him. Anybody from Wyoming, of course. Director of the Wind Energy Research Center, but he did go to Penn State, so I felt pretty good about that, knowing a few people from over there. I read through the document here, and there's a lot of interesting engineering stuff that really went over my head, but I noticed the turbulence research, and I actually thought for a minute that he was talking about California politics, but no, it wasn't that. So we're going to hear more about what he was talking about. It's perfect, though, for Wyoming wind resources. But I think the real reason, having had dinner last night with Jim and Jonathan and his wife, that he came to Wyoming is for the skiing. It just so happened that he had the perfect data set, so to speak, to make a difference here. But I really think it was the skiing that got him here, and I won't say kept him here, but it sure is a good reason. So without going any further, I want to introduce Jim and get him started on wind diversity enhancement of California's renewable energy production. It seems like a big duh to me from California, but we've got a lot of convincing to do. So,
thank you, Danny. Appreciate the introduction. So I'm going to start out talking about this project that now has been going on for about 3 years, and Jim Detmers is going to pick up and talk about it, and then Jan will also discuss some of the feedback that we're getting on the project. It grew out of a discussion at a coffee shop about 3 years ago about, people were discussing about capacity factors and how good wind was, but people weren't talking about how different resources play together in the electric market. Partially because, the use of wind is relatively recent. The time constant in the power industry is about 100 years, Jim, is that right? And renewable energy's only been around, really in an active way, if you say hydro out of the picture, for about 30 years, and in a significant way, as you'll see in a minute, just the past 10. So we started that conversation, and it kind of evolved over time, and then the conversation got a little more interesting. About a year ago today, Jim and Lloyd and I were sitting in a lobby of a Holiday Inn in Sacramento, California, and we started talking about ways to try and translate some of this diversity into ways that people could understand and how people could use the information to inform decisions. And so that's what this work's going to be talking about today. So again, just a quick outline. What I'll do, I'll talk a little bit about our previous work. This is a phase 2 study. Obviously, I'll pick up on our work, but others that's going on. Talk a little bit about our objectives of what we're trying to accomplish here, and then our approach, specifically talking about these renewable energy quality metrics that Jim and I have been working on for about the past year. I'll go through the scenarios that we're going to kind of use to demonstrate how these types of quantities could be used to inform decisions. And then we'll talk about results and go into our conclusions. And then I will take a little bit of time to do some acknowledgments, because there's a lot of pieces to this that wouldn't have happened if people weren't generous with their time and their information. So again, this audience is pretty informed of this, but just to make sure everybody knows how fast wind has grown. So in the United States, it was 0.3% of our electricity production in 2003. And as 2013, it was 4.3%. Today, it's right around 5%. So you think about how fast that is in the power industry to have gone from essentially nothing to a significant amount. And a lot of that has to do with California going into the wind market, Texas going into the wind market, the middle of the country going into the wind market, including Wyoming to a degree. So if you take a look at what's coming out in terms of it, and I would recommend there's some good material in the 2015 Annual Energy Outlook from the EIA, which is a clearinghouse of information for energy from the Department of Energy. You know, there's a lot of things that are pushing renewables. It's not just one thing. So retirement of coal-fired generation we just heard about. There's a lot of that going on, which means even in the absence of growth of demand, we've got a need for putting that, we got to make up that supply. We've got increased renewable energy portfolios in states. California is right now discussing a 50% renewable energy portfolio. Elimination of once-through cooling along the California coast, again, is a thing that's going to affect a regional effect. And then the other thing that's really happening that we've probably seen that nobody maybe expected was going to happen quite as fast as it did is the reduced cost of renewables. And when I'm saying reduced costs here, I'm simply talking about the cost to produce energy, not to include it into the grid, which is where the sticking points come, right? So all those are good things, but what happens is as we start to include more and more renewable energy into the grid, this little fact that we have not dealt with variable supplies of energy, variable just meaning we don't dictate all the time when the wind's going to blow. We don't dictate even how the sun's going to behave. You think that that's pretty deterministic, but we know it's not going to happen at night. And then we can't help when clouds come over, and this has big effects on it. So that's a new thing for the power industry. That's not something in the past. We just created the energy we needed to meet demand, and that's where it ended. So that's new, and we've got to figure out ways to mitigate that variability as it increases. If we're going to go from 4.3% of wind, and if you add that to other types of renewables that are variable, solar primarily, you know, we're sitting around 6%. If we go from 6% up to 30%, what happens to how you operate the grid? What happens to pricing? What happens to the transmission that you need? So these are all things that have to be addressed. One of the ways that has been talked about, and it's not new, people have discussed this, is the use of diversity. And I'm going to spend a little time in diversity because when I've given these talks before, people said that was a really interesting talk, except I didn't go away with an idea of what this diversity is. So we'll chat about that in a minute. So let's go right into it. So the idea of diversity is that it captures the interaction between variable supplies, all right? So if you look at one supply, and up here you could take a look on the upper part there. I've got the capacity factor of California wind as a function of the time of year and Wyoming wind. And you can see that California tends to have high production in the spring and summer, and then it drops off in the winter and then comes back up, while as Wyoming tends to be lowest in the summer, goes up, and then decreases back in the summer again. So that's the idea of diversity. These things are doing different things at different times, and if we combine them, they look a lot different than if you just rely on a single resource alone. There's different types of diversity. There's resource diversity. This is the idea that, hey, if I put all wind in one location and rely on that, I'm going to have real variability issues. But if I maybe combine some wind with some solar, with some geothermal, that's going to produce a more consistent product. The other thing is what we call geographical diversity, and this is the idea that if we take wind not from one location, but we take wind from a very large location, and you can think about, for instance, when you look at the weather, how a storm passes across the United States, generally high winds are associated with storms. So it means as that storm goes across, the wind's going to be high in different places at different times. If we can integrate all those areas together, the product that you get out tends to be more consistent than if you looked at any one location at all. And it's kind of like spreading your bets, right? You have more assets out there that can capture things, and therefore, in general, they produce a more consistent product. So we are not the first. Again, we about 2 years ago, we presented the phase 1 part of this effort that discussed how we could identify areas with diverse resources, and then gave some examples, and it was kind of starting the conversation. Since then, there's been 2 interesting reports that have come out, one by E3 and one out of Lawrence Berkeley National Labs, that looked at specifically diversity and how it would affect the penetration of renewables further into our supply. So kind of the highlights of that work, just going through it because I want to get to the new stuff. Methods of identifying diverse sites were considered. Examples of potential benefits of combining diverse sources was discussed and shown, demonstrated. One study looked at overproduction and curtailment under different scenarios and showed that geographic diversity tended to reduce those things. And those are both negative aspects of renewables. You do not want to have oversupply or curtailment if you can avoid it. Capital investment and revenue requirements were reduced in one study. And then the economic value of variable generation was preserved if you use geographical diversity as the concentration of those resources increased. And this is just basically the idea that as you add more and more of one thing and it has the same variability, it gets harder and harder to use that, and therefore its value goes down. So these are just an example of some of the results, and I encourage you to look at these different reports because we're looking at this a slightly different way than they have. So despite those positive results, I think it was a good start in all those cases. There's still some good questions out there. The first was kind of following up on our initial report, was looking at, we use model data in that. We wanted to go back and question, well, is model data, particularly for wind, really reliable enough? There's known problems with the current tools, which are basically your weather forecasting models, of capturing winds accurately. So we wanted to make sure that we address that. Can the effects of diversity be usefully quantified? There's different applications that people want to know. What is this diversity? Are you a ratepayer? Are you a utility? Are you a system operator? Are you a supplier? So we wanted to figure out ways that we could quantify it for those audiences. And to that end, we asked the question, can variable resources be characterized by metrics that go beyond kind of what would have been considered standard in the past, which is something like a capacity factor. How much energy are you producing over what you could if you ran 365 24/7, right? So that's what we really have to deal with, these variable resources. They're new beasts. And then can the benefits of diversity, I've already said this, but be translated into benefits for the consumer. So the objectives of this specific work were to demonstrate that our previous work using model data was actually showing the correct trends. And then we got done with that and we said, okay, great, it works. And so what? How do we communicate what these are? And that's when we got into this set of metrics that Jim and I have been working on for the past year. So we'll talk about those metrics quickly and then apply them to a couple of examples to show you how they can be used. And then we'll do some demonstrations of the benefits of diversity, some examples. Again, this is a very This is a first type of a study, so I don't want to say that these are the be-all, end-all type of numbers, but they're going to show you the type of analyses that this framework can actually enable. So our approach was actually to go out and get data. Now, for those of you who've worked in this industry long enough, this is a whole task in itself, not just working with the large voluminous data you got to get, but actually getting people to agree to give you data that's often considered sensitive for different issues. So we were very fortunate that we were able to have developers in Wyoming provide us wind energy, and then we were able to get the data we needed out of California through the California Independent System Operator. And I will thank those groups towards the end. I have a whole acknowledgement slide where I'll single out those people. So anyway, we also had to get out of one of the wind turbine companies some power curves that we can convert our wind to power. Now that sounds pretty simple, but it's actually a little more complicated than it sounds because there's density variations throughout the years. It's not just a single simple conversion. So we actually spent some time and worked with one of the turbine manufacturers to actually get realistic outputs so we could do that. So what we were able to do at the end, rather than going through all this in detail, was we could get an estimation of power that would come out of Wyoming based on these wind anemometer readings that we have. And then we could look at that and compare it to what's actually going on in the California grid with their renewables. And specifically, we looked at wind and solar on California ISO's grid, and then some assumed geothermal. I do want to mention that the data from Wyoming was distributed across southeast Wyoming, which is the wind energy producing area of Wyoming, and the data from California was from across California. So we didn't cherry pick this to get an answer that we wanted to. So we took data from a one-year period, June of 2012 through May of 2013. I put one equation on there to prove that I'm academic, but that's the last one, I promise. We looked at diversity as characterized by the correlation, and if any of you have seen my talks before, that's where a lot of that focus. But basically the idea is if you perform this correlation, what we want to interpret in terms of diversity is that when you have low correlation between power produced at different sites, that's good for diversity. That means you're producing power at different times. When you have high correlations, it indicates that everything's producing power at the same time, and that would indicate a lack of diversity. So when the numbers are presented on correlation, remember low, good, high, not so good, okay? Which is the opposite of many of the other metrics. So I just want to point that out. And then we went ahead and took a look at the effects of diversity evaluated in these renewable energy quality metrics. And Jim's going to talk about these also, but I'm going to go through them quickly, and Jim will probably also do that. We didn't converse as much as we should have about our presentations, but I'll go through them quickly, and then Jim can either fill in what I missed or skip over those slides. And then finally, we'll do some examples that look at when you do use diverse resources, what are the benefits in terms of production, in terms of greenhouse gas emissions, in terms of water use, and at the end of the day, in terms of price, okay? So that's kind of where we were going to go. So I want to talk about first is these capacity factors, and I said there was only one equation. I lied. There's more equations, but there's also a graph in here that I have to explain, but I think it's pretty straightforward to actually do that. If you take a look at this graph, what this represents is this is a histogram of the power that was supplied by a given set of resources, okay? So sometimes you produce a lot of power. One means that you're putting out 100% of power from all those resources, okay? And down here at some point, you notice it never goes to zero. And it never goes to zero in this case because I have some kind of something that's on all the time. In this case, it was geothermal power was on all the time. But what it's basically showing you is if this was geothermal, solar, and wind, is that you get a range of production that's all over the place. This is the variability. So we have to characterize this. And so we characterize it right now. I'm going to talk about 4 metrics, and Jim may talk about some of the newer ones he's working on. But basically, the one that's been used in the past is the capacity factor. And the capacity factor is this one right here in the middle. What's the average power being produced by this, right? It doesn't talk about anything about the distribution, how wide it is. It just talks about what's the average power. And it's actually the average power divided by the maximum power. So it's a number between 0 and 1. And to give you an idea, a typical great capacity factor for wind is a 50% capacity factor, or 0.5, okay? And we have sites in Wyoming that actually exceed that. So it's not it's not uncommon to have 40, 50, 55% in really good wind producing areas, all right? But that's what's been used in the past, okay? One number. But again, remember, it didn't cover this idea that there's a variation of this power, okay? So Jim and I, discussing this a year ago again in a Holiday Inn, came up with this idea of relative variability. We probably called it something different at that time, but that's what we came up with as a name, or I did, I can't remember. But the idea here is it characterizes how much spread there is in this distribution. How much is the thing varying? And it's essentially if you've taken any statistics, this is the standard deviation divided by the error, or divided by the average, sorry. So if you're in electronics guys, this is a signal to noise ratio. It's basically a measure of how much is varying to how much the average is, okay? So it gives you an idea of how consistent the output is. So in terms of this, a low number is good. We'd like to have low variability, all right? Now, another couple of metrics we came up with represent how often is this actually producing power, right? Because if something drops out entirely and isn't producing power, that thing can be relied on less than something that is producing power a reasonable amount of time. So the idea here was to come up with some metric that described that it was going to be producing power some amount of time. So what I'm calling the P greater 5 is that it's putting out more than 5% of the installed power. So this red line, everything above to the right of this red line would be the P greater than 5. In this case, it would be 100% of the time, okay? Another metric is the P25. This is when it's producing more than 25% of the capacity. So this could be inferred as it's producing this amount of power, which is a significant fraction of its total. So the P25 would be everything to the right of that purple line there, all right? So, and both of these numbers, the higher they are, the better, all right? So we're going to take a look at 3 different scenarios here, some where we're just combining wind, Wyoming and California wind, a second where we're looking at Wyoming wind and California renewables, and this is based on a report that's actually you've seen here that was presented by NREL, which is on the California-Wyoming Grid Integration Study, using their scenarios. That I just used their straight scenarios here with California resources or Wyoming wind. And then the final one we're going to do is where we use 33% added to existing California renewables. So we look at just the existing. What if California added more of the renewables that they've already got, wind and solar out of California, and the last one would be Wyoming. So I'm going to look at this correlation stuff really quickly. The bottom line of the correlation and the results was what we saw in the original study was borne out here. Things in the same area, so this is Wyoming in the light green, they have high correlations with each other relatively. California down here, a little bit less correlation with themselves because this is, again, it's over a little bit larger area from Northern California to Southern California. You can see high numbers pop out here. But the real thing here is when you look at California correlated with Wyoming, consistently you see lower correlations. Remember, lower correlations means more diversity. Good. Well, perhaps more than important than this, and pointed out by Jan sitting here next to me, is that maybe the most important thing is not to consider how they're correlated with each other, but how they're correlated with the existing wind on the California grid. And that's what this is. So these are the Wyoming correlations with California's existing and California sites correlation with existing. And again, what you see is consistently the Wyoming numbers, because of this geographic diversity, are lower. This is not an astounding type of result. It's kind of what we expected, but it's just comforting that you get what you expect. Sometimes that doesn't happen. So if we look down here, we've got this relationship that these things are diverse. Well, the question came up, all right, correlation can be used as a screening basis, but how does this better diversity that we've identified, how can we turn that into, well, it's not just a correlation number. What does that mean in terms of the operability, in terms of developing resources or using them? So here's some of the examples I'll give. So this is looking at a California-Wyoming wind scenario, 100% of a California installation. This is one wind farm, 100% of a Wyoming installation. And if we look across here, we have all these metrics. We see capacity factors, we see the relative variability, and we see these P greater than 5 or P greater than 25. Remember, all these numbers, as the relative variability goes down, that's good. Everything else we like high, okay? Now, if we take a look at it, I don't want to focus on the individuals here. What I want to focus is when we mix those two things, boop, down to this line, the bottom one, notice the capacity factor is actually the average of the two, okay? So this is not, the capacity factor is just going to always be the average. What we want to look at, though, is look at the relative variability dropped significantly from what the two other cases were, and the P greater than 5 and the P greater than 25 go up significantly. These are what we want to see. These are purely effects of the diversity that we're saying things are getting better. Aside from just adding better or less good wind, we're looking at how these things combined actually perform better. And they always perform better when they're diverse wind sites, when you see these things. All right, so that's a Wyoming wind, California wind. Let's take a look at Wyoming wind combined with, as NRO looked at, not just Wyoming wind, but looking at wind, solar, and geothermal out of California compared to Wyoming wind. Now, this isn't compared to the existing. This is just what they would be. And again, what we see is there's slight increases in all these cases of, I should say, slight increases in the P25 and P relative variability goes down, which is good. P greater than 25 goes up, looking from California to Wyoming. The only thing that is higher in the California scenario is this P greater than 5, and that's because of the geothermal. Think of geothermal as like on demand. They can turn that on and off at will. But that's probably not as important as if we look at adding that capacity to existing California. So here's existing California, and what we find out is we've got a relative variability of 0.59. When we add in California resources, that's the second line, the relative variability goes up. Why does it go up? Well, you're adding more of the same resources that have the same kind of behavior, and that's why you do it. When you add Wyoming wind, the relative variability goes down, all right? The P greater than 5 is 1 in all these cases, and that's again because of the geothermal. But look at the P greater than 25. It goes, when you go from California existing to adding more of the same resources, it actually drops, all right? And that has to do with the combination you're adding. It's not as exact, it's not the exact mix that you have on there now. But when you add in Wyoming wind, the P greater than 25 goes up significantly. So again, just showing that you can use these metrics now to compare these different resources. Let me go over just quickly, because I know Lloyd's going to want us to move on here quickly, but let me go over some of the scenarios just to show you some of the benefits, okay? One of the benefits is, let's say we had a fixed amount of capacity added, or you could think of this as a fixed capital investment. If we added 6,000 megawatts, we could put it all in California, or we could distribute it. And what we did is we looked back, I'm going to back up here, we looked at the differential power produced at different times by different scenarios, okay? And you can add up that differential over the entire year, and you can come up with the fact that when we combine things, I use California as a baseline, when we combine it with California with Wyoming wind, we produce more energy. That offsets backing power that you have to do. So that's the cost of what that backing power would cost based on basically gas-fired generation. That's the CO2 that would have been emitted from that generation, and this is the water that would have been used. So just to get the idea that the benefits of this are reduced cost, reduced CO2 emissions, and reduced water usage. And just to give you an idea that this is, you know, something significant, that 1 million tons, all right? So we've got over here, this is 1,000 tons, so that's 2 million tons there, right? 1 million tons represents 193,000 cars on the highway for 1 year, okay? That's not trivial. The water's not as big a deal. It's 1,500 Olympic swimming pools, but I expect you go to certain places in California right now, 1,500 Olympic swimming pools is considered a lot of water. So, okay, I'm going to skip over a couple things. Last thing I want to talk about is storage, because right now one of the mitigation strategies talk about is storage, and certainly energy storage is going to play a bigger role. But one of the things that diversity does is it reduces the amount of storage that you need. So even though you're going to build it, you can build less. So this was a scenario where I have, here's an output from a scenario where I've got a series of renewables. And notice the spikiness of this. Guess what that is? That's a lot of solar, right? So every day, middle of the day, you got a lot. At night, you don't. And then I created a simple demand where we had a fairly constant demand during the day and very low demand at night, and it just cycled, just as an example of how you would do this. And this is a simulation where we start out with some storage, and then because we're not producing as much, we drop storage, and then because we're producing more, we get the storage back up. That's what storage is. It's just a bank, right? You put energy in and you get energy out. All right, so here's the numbers that come down. And what I did is I looked at what if we were doing, just as an example, 1,000 megawatt hours of production a month, okay? And I looked at a December and a June kind of that's a winter and a summer scenario. And I looked at how much storage you would need to keep that average power. In other words, the storage could never go below 0. And remember, this is just 1 month of data, just looking at it once. You'd have to do this more. But we look at California's existing, you'd need 60 gigawatt hours of storage. It drops as you add new California resources, and that occurs because the better quality of those newer installations is always there. But it drops even further when you add Wyoming resources. And again, same thing in June, maybe even more stark, is you get from 46 down to 35 when you use Wyoming. That represents 6 to 10% reduction of all California resources. And if you use the numbers that are kind of quoted for storage these days, the cheapest storage is pumped hydro, okay? That represents 300,000 to 400,000 a month. Just that 6 to 10% drop, okay? So these are, again, starting to be real numbers when you do that on an annual basis of how much that would be. So, again, just some conclusions, key findings in general. We think we've got an exciting framework here for analyzing renewable energy that we think has some legs to it. We need to do some more work. Jim's going to talk more about how it could be applied specifically to system operators and utilities. But we think we've got an exciting thing that's going on. We've also been able to show some examples of diversity. I also think that specific to the Wyoming, California renewable resources, we're really starting to show that, you know, besides just better quality wind and money savings due to that fact that we have higher capacity factors here, there are other implications of blending wind between Wyoming and California that's good. Or if you want to generalize that to blending resources from across the West to provide a better product of renewable energy is really going to help out the entire West, because you can even imagine California in the middle of the summer during the noontime when they have all that solar, there's people that need that power that would be shipping it back. So this idea of sharing these resources is great. So again, lots of examples there. Finally, just to say again, and I'm going to let Jim talk about this, I really think it's this framework that's kind of excited. We've started the idea that can we have a thing where it's not just capacity factor, but where it's really what blend of resources can we bring to bear on a specific problem that are going to give it the best quality product it can, noting that diversity is not the only thing that's got to be considered. There's cost, there's other operability type of issues, there's things that the utilities themselves have to meet regulations, the system operator has to meet regulations. So finally, I just want to thank all the people that are involved, Power Company of Wyoming and Pathfinder Wind for providing the wind data, specifically Ryan Jacobson and Holly Wold, who actually sent the voluminous amounts of data that we needed. General Electric provided us the information on the turbines so that we could get realistic wind turbine outputs. CAISO, David Timpson and Clyde Lutan there, who provide us information on the pricing, wind, solar, you name it. And then up here, I want to thank Jim and Jan, and also Lloyd Drain for Lloyd's really pushed this and kind of has had us make some good conversations that may have led us in directions we weren't thinking we were going. And then also David Smith from Power Company of Wyoming for his feedback on this. And the report that will be coming out in the next 7 to 10 days is much improved due to these people's comments. Thank you.